Ladies and gentlemen, once again I bring to you another episode of our hit SolveIt series, where we look at complete past paper solutions with explanations that a mere mark scheme or examiner report will not give you. It's a quick revision of the entire syllabus with a look at the latest paper formats. And in this episode, we will be looking at the latest May-June 2022 MCQ paper for A-level chemistry 9701. So for those of you who are appearing in October-November this year or appearing next year, this will be a useful guide to what happened in the first paper of the new 2022 syllabus. So without further ado, let's get started. Assalamu alaikum everyone, this is Fahad Ansari and I'm here to help you conquer chemistry. So before we begin today's video, just a reminder that most of you still haven't subscribed to this channel. So before we begin this video, do subscribe, push the bell button for notifications, and without further ado, let's begin. So the first question of the May-June 2022 Paper 1 Variant 2 of the A-Level Chemistry syllabus was regarding certain enthalpy changes. So equations involving 4 enthalpy changes are shown, right? And it says which equation represents the second ionization energy of sodium, right? So second ionization energy is what is asked for, right? So if I look at the first equation, you could see 1 mole of gaseous atoms is being converted into 1 mole of gaseous 1+ ions. So this over here would be the first ionization. So this is the first ionization energy of sodium. The second equation involves 1 mole of gaseous atoms being directly converted to 1 mole of gaseous 2+ ions, right? So this enthalpy change actually involves the first ionization where the first electron is removed and the second ionization where the second electron is removed, so that you go directly from atoms to 2+ ions. So this enthalpy change involves the first and the second ionization energies. And so what I could do is simply subtract from X the value of W, which is for the first ionization energy. So this will give us the second ionization energy. So X minus W will be the value of the second ionization energy of sodium. So in question 2, it refers to isolated gaseous atoms in the ground state. So in which atom are all electrons paired? Now, one thing that you might be tempted to do is to write out entire electron configurations for all of these atoms. Well, you don't actually need that. All you need is the number of valence electrons, which we can get from the group numbers. So barium, if you check this out, this is in group 2 of the periodic table. And so its electronic configuration, because this is in the S block, its electronic configuration will end in S2, right? So the last electron is actually part of an orbital where an electron already exists, and so they are in a pair, right? So if the last electrons are paired with each other, that means all the electrons before it are also paired by default. So you don't even need to look at the remaining options. Option A is going to be correct for this one. So which sample contains the most iodine, right? Now, this might be a little ambiguous, this language. Which sample contains the most iodine? What this essentially means is that which of these compounds has the highest percent by mass of iodine, right? And the reason why I say this is because you have the same masses of all 4 compounds. You have 1 gram of each of these, right? So I don't need to find the exact mass of iodine in each of these masses of the compounds, but all I need is the percent by mass, right? So what I will do is I will show how to do this for a couple of these options and then just write down the values for the rest. So for option A, I have calcium iodide. So what I will do is in the numerator of this fraction, I have 2 iodine atoms. So 2 times 126.9. 126.9 is the AR of iodine. Divide this by the MR of the entire compound. So this will be calcium, 40.1 is the AR, plus 2 times 126.9. And if I multiply this by 100, this will give me the percentage by mass, which turns out to be around 84%, right? So this is for option A. And if I go to option D over here, if I go to option D, this is ammonium iodide, right? So for ammonium iodide, I have 126.9, that is the mass of the one atom of iodine, divided by the mass of the entire compound, the MR, so that's nitrogen, 14 plus 4 hydrogens, that's 4, plus 126.9, and we multiply this by 100% again, and this turns out to be 87%, right? For the other two options, this is actually 76%, and this is 86%, right? These are rough values from what I remember, and you can figure out these values yourself based on the calculations we've done for options A and D, and you can clearly see that the highest percentage by mass of iodine belongs to ammonium iodide, so option D is going to be correct for this one. So when a small sample of hydrocarbon Q is completely combusted, now when this is completely combusted, we have a hydrocarbon, we are going to have carbon dioxide and water as our products, right? So it produces 3.52 grams of CO2 and 1.44 grams of H2O, right? What could be the structure of hydrocarbon Q? So the first thing to do over here is to find the moles of carbon dioxide and water. So the number of moles of CO2 is very simple. We do mass over MR, simple formula. We have 3.52 divided by 44, which is 0.08 moles. And similarly for water over here, NH2O, again we use mass over MR, and this is going to be 1.44 divided by 18, which is also 0.08 moles. So you can see over here that the ratio of carbon dioxide to water is going to be 1:1, okay? So when I write the equation, I'm going to write 1 mole of carbon dioxide and 1 mole of water in the products to respect that 1:1 ratio. And of course, the hydrocarbon is going to react with oxygen. And over here, the carbon in carbon dioxide comes from the hydrocarbon, and the hydrogen of the hydrocarbon goes into the water, right? So we have 1 carbon and 2 hydrogen atoms on the right-hand side, and so I can write an empirical formula, if you will, of the hydrocarbon, which is CH2. So this is an empirical formula of sorts, right? And if you want to balance out this equation, we have 3 oxygens on the right, and this will be 3/2 O2 on the left, right? So we have CH2. Now we need to find a compound which has this empirical formula of CH2. Now this CH2 is basically the empirical formula of either alkenes, which have 1 carbon-carbon double bond, or of cycloalkanes, right? Which have the general formula of CnH2n, right? Now, out of all of these options, we do have alkenes over here and over here. But option A has more than one carbon-carbon double bond, and so it will not respect the CnH2n. If I were to write its formula, I have 1, 2, 3, 4, 5, 6 carbon atoms, right? And because each of these carbon atoms is involved in a double bond, so it'll only be bonded to one hydrogen each. So this is C6H6. So the empirical formula is just CH. So it's not going to be correct. For option D, if I count again, I have 1, 2, 3, 4, 5, 6 carbon atoms, right? Now, the 2 carbon atoms over here and here, which are part of the double bond, will be bonded to one hydrogen each. And the remaining 4 will be bonded to 2 hydrogens. So that basically means that we have 2 hydrogens here, 2 over here, 2 here, and 2 here. So that's 8 plus 1, that is 10. So C6H10 gives an empirical formula of C3H5. So again, incorrect, right? So that leaves us with these 2 options. Now, option C has carbon-carbon triple bonds. Now, this is neither an alkene nor a cycloalkane. This is an alkyne, right? Option B, on the other hand, is a cycloalkane. So I'm going to go with this one. And just for insurance purposes, let me look at its empirical formula. We have 1, 2, 3, 4, 5, 6, 7, 8 carbon atoms. And each carbon atom will be bonded to 2 hydrogen atoms. So that's C8H16. So that is CH2, which is the empirical formula, which is what we want. So option B is going to be correct. Now, ethane and ethene, you have studied these very well. Ethane is C2H6. It looks something like this. We have 2 carbon atoms. Each is bonded to 3 hydrogen atoms, and the 2 carbon atoms are bonded to each other by a single bond. Now, what is a feature of both molecules? Now, a planar structure does not exist for ethane. The reason is that each carbon atom is bonded to 4 other atoms, and it has no lone pairs, so the bond angle will be 109.5 degrees, and the shape will be tetrahedral, which is a 3-dimensional shape. It is not planar, right? So planar will not apply to ethane, right? Bond angles of 109 degrees, this applies to ethane, as we have already seen, but for ethene, it does not apply. Because ethene, we have a carbon-carbon double bond. And each carbon atom is bonded to 3 other atoms, and there are no lone pairs, so the bond angle will be 120 degrees instead, right? And the shape actually turns out to be trigonal planar, right? So ethene is a planar molecule, but ethane is not, right? And on the other hand, bond angles of 109 do not exist for ethene. Sigma covalent bonds and pi covalent bonds. Now, pi covalent bonds only exist for ethene because you have a double bond over here. You do not have any double bonds in ethane, so there are no pi bonds. But sigma bonds are present in every single covalent compound, so option C is the correct way to go. All right, so the next question is about elements J and L, which are in group 15. So it says over here that J and L each form a gaseous covalent hydride in which the oxidation number is -3. In the liquefied forms of these hydrides, significant hydrogen bonding occurs only in the hydride of L, right? So now in the identity of J and L, we have 2 options, right? Either of them could be either arsenic or it could be nitrogen, right? So we know that nitrogen is pretty much at the top of group 15 and arsenic is below nitrogen, right? And both of them form hydrides in which their oxidation state is -3. And we know that hydrogen usually has an oxidation state of +1, right? So 3 times +1 will balance out the -3 to make the overall oxidation state of the compound 0. So this will mean we have NH3 and we have ASH3, right? So it says in the liquefied forms of these hydrides, significant hydrogen bonding occurs only in the hydride of L, right? So out of these two, nitrogen is obviously more electronegative. In fact, it is amongst the three most electronegative, F, O, and N, these three elements, fluorine, oxygen, and nitrogen. And if we have a nitrogen bonded to hydrogen, that will result in hydrogen bonding between the molecules. So that tells us that because we will have hydrogen bonding in NH3, so L is going to be nitrogen, right? So identity of L is going to be nitrogen, so it's going to be either option A or B, right? Now it says outer shell electron configuration, right? So this is group 15, right? So that means that we have 5 valence electrons. So 5 valence electrons will be distributed in the outer shell such that in the outer shell, the S subshell gets 2 electrons and the P subshell gets 3 electrons, right? Remember that group 15 is in the P block, right? And so the last electrons need to be in the P subshell. But over here, there can be a bit of confusion, right? Some of you might be tempted that, because it's in the P block, the outermost subshell is the P subshell. So all 5 valence electrons go to the P subshell. That is not correct. The outermost shell has an S subshell, which gets the first 2 electrons, and then the P subshell, which gets 3 electrons. And so it's going to be option B for this one. Which gas will behave least like an ideal gas at 150 degrees Celsius and 101 kilopascals, right? So which of these is the least ideal? In other words, which of them has the strongest intermolecular forces, right? So when you have stronger intermolecular forces, that means ideal behavior will be less, right? Because ideal gases usually have negligible intermolecular forces. Right, so out of these, we know that fluorine exists as diatomic molecules, right? And so because these are non-polar, and so this will result in instantaneous dipole-induced dipole forces, or IDID forces for short, which are the weakest type of intermolecular force. Krypton is a noble gas, right? It is monatomic. So again, this will be instantaneous dipole-induced dipole forces between krypton atoms, right? So that leaves us with ammonia and steam. Ammonia, we saw it has hydrogen bonding in the previous question, right? This is hydrogen bonding for this one. And steam also has hydrogen bonding. Steam H2O also has hydrogen bonding. So now how do we decide between these two? Well, one way to decide between these two is to first look at the number of molecules that an individual molecule can bond to at the same time, right? Now NH3 over here has 1 lone pair on the nitrogen atom, right? So this 1 lone pair can attract a partial positive hydrogen in another ammonia molecule. It can only do this for 1 other molecule, right? But in the case of water or steam, we have H2O. The oxygen over here has 2 lone pairs. So each lone pair can attract a partial positive hydrogen of another water molecule. And so each molecule of steam is bonded to 2 further water molecules or steam molecules. And so the hydrogen bonding is more dense, you could say. There is a more extensive hydrogen bonding network because each molecule bonds to two other molecules by hydrogen bonding. In the case of ammonia, that's only one molecule bonding to just one other molecule by way of the lone pairs. So steam is going to have the strongest intermolecular forces, and so it will be the least ideal. When an evacuated glass bulb of volume 200 cubic centimeters is filled with a gas at 300 Kelvin and 101 kilopascals, the mass of the bulb increases by 0.68 grams. The gas obeys the ideal gas equation. So the ideal gas equation is PV equals nRT. And because it's asking for the identity of the gas will be found by finding its AR. The reason why I'm using AR is because three of these options are monatomic noble gases, so we will use AR. But for nitrogen, we have MR, and so we could go with either of these terms, right? So the moles over here, N, can be replaced by M over MR, mass over MR, or mass over AR, whatever you want to use, right? So we will modify this equation. So we want to make the AR or the MR the subject of this formula, and so this will become MRT divided by PV, right? Now we just plug in all the values. Mass is 0.68. Now remember, we need to keep this in grams because when we use mass over MR, we use mass in grams, and so it will stay in grams. We do not need to convert this into kilograms. This will be 8.31, the ideal gas constant, and we have temperature 300 Kelvin, the SI unit, we don't need to convert this, divided by pressure. Now pressure is in 101 kilopascals, so we need to convert this into pascals, so we multiply by 1000, and we multiply this by volume, so this is 200 cubic centimeters. We need to convert this into cubic meters, so we divide this by 10 to the power of 6, because remember, each meter has 100 centimeters, right? If I cube both sides, I'm going to get 1 cubic meter will be equal to 100 cubed cubic centimeters, which in other words is 10 to the power of 6 cubic centimeters. So once I solve this entire thing, the AR or MR, whatever it is, comes out to be 83.9. Now I'm going to check the periodic table and see if either of these noble gases has an AR of 83.9. Turns out that it is actually krypton. So it's going to be option B. It has been identified using its AR that we calculated from the ideal gas equation. The standard enthalpy of formation has been given for NO2 and N2O4, and we have this equation that converts NO2 to N2O4. Right, so whenever we want to find the enthalpy change of a reaction that with the enthalpy changes of formation given for the reactants and products, the formula is simple. We're going to sum up the enthalpy changes of formation of the products, and from that we will subtract the sum of enthalpy changes of formation of the reactants. And so in this case, the product is N2O4. Its enthalpy formation is 9.2 kilojoules per mole. So that's 9.2. From this, we subtract the sum of enthalpy changes of formation of the reactants. We have NO2, whose enthalpy change of formation is 33.2. And we have 2 moles of it in this equation, so we will multiply this by 2. So 2 times 33.2. And so the answer turns out to be negative 57.2 kilojoules per mole. And so that will be option A right here. And over here we have a question to think about. It says over here we have separate samples of 25 cubic centimeters of 0.1 mole per cubic decimeter sodium hydroxide, which are added to each of 3 different acid solutions as described, right? So you have 3 acids. We have sulfuric acid, we have hydrochloric acid, and we have ethanoic acid, right? And it's also been mentioned that ethanoic acid is weak. We have been given the concentrations and the volumes, right? SolveIt statement describes the temperature rises that occur in mixing each of these three acids separately with NaOH, right? Now the thing is that whenever you have an acid-base neutralization, the enthalpy change associated with this equation will be the enthalpy change of neutralization, and that is always associated with the moles of water being formed, the hydrogen ions from acid plus hydroxide ions from the base, that will give us water. And the enthalpy change of neutralization, it depends on this guy, right? The number of moles of water that will be formed will dictate the amount of energy released. And I say released because the ions are bonding together, so bond formation is exothermic, so enthalpy change of neutralization will always be exothermic, right? So that results in the temperature rise in these surroundings because of the exothermic nature of a neutralization reaction. Right, so we need to find the number of moles of water formed in each of these three cases. So 25 cubic centimeters into 0.1 mole per cubic decimeter, 0.1 divided by 1000, so that we have cubic centimeters in both volume and concentration. So volume times the concentration will give us the moles of sodium hydroxide. All right, and so this turns out to be 0.0025 moles. All right, so we have NaOH, and for all of these acids, obviously the moles will be half. The reason is you have the same volume, but you have half the concentration for each of them, and so the moles will also be a half, right? So we have NaOH that reacts with H2SO4. That gives us Na2SO4 plus H2O. So if I balance this equation, turns out that I'm going to get 2 NaOH and H2SO4, right? So I have 0.0025 moles of NaOH, and half of this would be 0.00125, right? And that is exactly the number of moles of H2SO4 that I have. I have 0.00125 moles, right? So both of them will react completely, and so I'm going to get 0.0025 moles because NaOH and water are in a 1-to-1 molar ratio. So I get this many moles of water over here. So this will give me 0.0025 moles, right? Now, without going into the details, we know that NaOH and HCl will react in a 1-to-1 ratio. So 0.0025 moles of NaOH, if it reacts with 0.00125 moles of HCl, then the thing is that we need to figure out which is the limiting reactant, right? So because they have a 1-to-1 molar ratio, if I have 0.00125 moles of HCl, I need to have 0.00125 moles of NaOH, but I have more than that, right? So HCl will be the limiting reactant, and so because HCl and H2O are in a 1-to-1 ratio, so I'm going to get 0.00125 moles of H2O. So already I can see that because I have more water formed because of H2SO4, H2SO4 reacting with NaOH in this case will lead to a higher temperature rise. And in the case of CH3CO2H, again, NaOH and ethanoic acid react in a 1-to-1 ratio. And again, we have the same 0.00125 moles of ethanoic acid. And because we have 0.0025 moles of NaOH that we have already seen, right? So that will result in ethanoic acid being the limiting reactant, and that will give us 0.00125 moles of water because again, ethanoic acid and water are in a 1-to-1 ratio. So out of all of these, it's the sulfuric acid that produces the most water, and so it will have the highest temperature rise or highest delta T. So out of all of these options, option D is going to be the correct one. Alright, so the next question shows a reaction between NCl3 and H2O. Says the oxidation state of nitrogen does not change in this reaction. So in other words, over here and over here, the oxidation state of nitrogen remains the same. In ammonia, we know that hydrogen has an oxidation state of +1. So this is 3 times +1, so that's +3. To balance this, nitrogen will be -3. And similarly over here, this will also be -3, right? Which means that we have 3 chlorine atoms over here, each of which have a +1 oxidation state to balance out the -3 oxidation state of nitrogen, right? And over here, if I look at HClO, we know that hydrogen is +1, oxygen is -2, right? Those are their usual oxidation states. And chlorine over here is also +1 to balance out the -2 over here. And over here in H2O, we have 2 hydrogens with a +1 oxidation state and a -2 for the oxygen. Those are the usual oxidation states. Right, so you can see over here that oxygen goes from -2 to -2. Chlorine goes from +1 to +1. Nitrogen stays the same at -3 and -3. And hydrogen also stays the same with +1 and +1. So you can see that no oxidation states are actually changing. So if no oxidation states change, this means that this is not a redox reaction at all, right? So just calculate the oxidation states and come to this conclusion rather than being confused by whether anything else is being actually oxidized or reduced. In which row do the oxidation numbers of vanadium increase, right? So over here you can see that the other element in all of these ions or compounds is oxygen, right? And oxygen has its usual oxidation state of -2. So in VO4, we have 4 oxygen, so that is 4 times -2. That's going to be -8. And because we have a total charge of -3, so we could write the equation x plus 4 times -2 equals -3. And so in this case, x turns out to be +5, right? So for vanadium, this is +5, right? If we do the similar calculation for VO3 negative, this is also going to be +5 because +5 plus 3 times -2, that's -6. So 5 minus 6 gives us -1, right? And in this case over here, let's write the equation for this. We have x for vanadium, the unknown oxidation state, plus 2 times -2 gives us +1, right? So x over here again will be +5. So over here, vanadium's oxidation state is not changing. Now, over here, VO2 positive was the case over here. Now we have a different ion, right? VO2 positive, right? We have a 2 positive charge. So if I write the equation for this, it's going to be x plus -2 because we have only 1 oxygen in this case, and this is going to be +2. So x over here turns out to be +4. So this is +4. And over here in V2O3, this is an ionic compound. And so if I apply the reverse crisscross method, right, I have V and I have O. So oxygen we know has a -2 oxidation state, and vanadium in this case would then have +3. So this is +3. So over here I don't even need to go further because it says that we need to increase the oxidation state. Over here it's decreasing. So this is going to be incorrect as well. So both first 2 options are incorrect. Now V2O3, we just found out this is +3 for vanadium, the oxidation state. VO2 positive, this was +4. We just found that out in option B as well. And in VO3 negative, this was this guy over here that we did in option A, don't need to repeat the calculations. This is going to be positive 5. So you can see that oxidation state is increasing from positive 3 to positive 4 to positive 5. So option C will be the correct one to go for. A synthesis for methanol is shown. Which conditions would produce the greatest yield of methanol at equilibrium? This is a very simple IGCSE style question, right? Now, over here we can see that the forward reaction is exothermic, right? Methanol is on our product side. So if I were to decrease the temperature, that would favor the forward exothermic reaction that will release heat and increase the temperature back up according to Le Chatelier's principle. And so I need a lower temperature. So I have two options, 80 and 20 degrees Celsius. I'm going to go for 20, right? Now for the pressure. Now we have 1 plus 3 equals 4 moles of gas on the left-hand side. And on the right-hand side, we only have 2 moles of gas, right? So the forward reaction decreases the number of moles, right? And we know that keeping everything else constant, if I increase the moles, I increase the pressure, right? They're both directly proportional, right? So if I want to go towards less moles, that will decrease the pressure. So what I will do is keep a high pressure at the start, right? According to Le Chatelier's principle, the equilibrium will shift to decrease that pressure. In other words, I need to decrease the moles of gas present. And so the forward reaction again will be favored at a higher pressure, right? And so this will be option B. So this next question is about equilibrium constants, right? This kind of question where you have moles of certain substances in an equilibrium, we need to find the moles of those substances once the equilibrium has been reached. So what I do is I create a table with the reactants and the products, and I have 3 rows. S for start, the starting moles, R/P for moles reacted or produced, and E for equilibrium moles. So over here it says 4 moles of hydrogen gas and X moles of iodine vapor are mixed in a sealed container of volume 1 cubic decimeters at a temperature 460 Kelvin, right? So these are the starting moles of hydrogen and iodine. So 4 moles of hydrogen at the start, X moles of iodine over here, and it does not say anything about the product, so I'm going to assume there is no product at the start. So the equilibrium mixture contains 2 moles of hydrogen iodide. So at equilibrium, I have 2 moles of hydrogen iodide, so that means 2 moles were produced, right? So if 2 moles were produced, according to this equation, the stoichiometry of this equation, if 2 moles are produced, that means I will have 1 mole of hydrogen and 1 mole of iodine reacting, right? So 1 mole of hydrogen reacts and 1 mole of iodine reacts, right? And so in equilibrium, once 1 mole has reacted, I have 3 moles left. And for iodine, I have X minus 1 moles left because these are reacted, so they're being used up, right? So now it says, what is the value of X? It says the equilibrium constant Kc is 4.0, right? So the Kc expression for this equilibrium is the concentration of hydrogen iodide, the product. This is squared because we have a 2 next to it in the balance equation, divided by concentration of the reactants multiplied with each other. They're not raised to any powers because you have 1s next to them in the equation. So I can directly input these equilibrium moles over here. The reason is the volume of the sealed container was 1 cubic decimeter. So if I divide the equilibrium moles by 1, I'll have the same value, but the units will be different. I'll have concentration instead. So Kc is 4.0. This is equal to Hi, so that is 2 squared, divided by H2, which is 3, and iodine, which is X minus 1, right? Now I just need to solve this equation. So this turns out to be, if I multiply this on this side, this is going to be 12x minus 12 equals 4, right? And so if I solve this further, this turns out to be x equals 4 plus 12 divided by 12. So that's 16 over 12, and that will be 1.33 moles of iodine at the start. So the value of x is option C. Right. So over here we have a graph being shown for the concentration of N2O, right? And this is the reactant in this case because it's being decomposed, right? And the concentration of the reactant you can see is decreasing with time, right? And we need to check two things, right? The change in the rate of reaction as N2O decomposes, right? Now this graph over here gives us the rate of reaction as the gradient. The gradient of this curve will be the rate of decomposition of N2O, or the rate of reaction, and you can see that this is constant because it is not a curve, it's a straight line. The gradient is constant, the rate is constant. So as far as change goes, there is no change in the rate of decomposition. Effect of adding more gold foil on the rate of decomposition. Now the question states that we have a gold foil catalyst, right? We have a gold foil catalyst, so obviously if you add more gold foil, it will increase the rate of reaction. So it's going to be option A. So you didn't even need to read the entire question. There's a lot of information in this, but there's only a little of it that is of good use to solve it. All right, so this is a question about the Haber process. And it says which statement is correct about this reaction when the temperature is increased. Now, notice that all these options are related to rates of reaction, right? So this is all about rate of reaction. This is not asking about position of equilibrium, right? So forget about everything Le Chatelier said and just focus on increasing the temperature. What effect does it have on the rate of reaction? It always increases the rate of reaction. Whether it is the forward reaction or the backward reaction, doesn't matter, right? So both forward and backward reaction rates will increase. Ammonia is added to separate samples of these chlorides, right? And it says over here that only 2 samples will produce a white precipitate when this happens, right? So the thing is that if I were to add ammonia, aqueous ammonia, to sodium chloride, nothing will happen. If I add it to magnesium chloride, what happens is that magnesium chloride is converted into magnesium hydroxide. And magnesium hydroxide is only partially soluble. And because it's partially soluble, it will appear as a white, cloudy solution, right? Or a precipitate. Sodium chloride, in the case of sodium chloride, obviously you will get sodium hydroxide, but because that's soluble, so you will not see anything. So that's why I said nothing happens, nothing visibly happens, right? And again, in the case of barium chloride, nothing visible will happen because barium hydroxide that is formed when aqueous ammonia is added is actually very soluble, right? The solubility of hydroxides of group 2 elements increases down the group. So magnesium hydroxide is partially soluble, whereas barium hydroxide is very soluble. In the case of silicon chloride, what happens is when I add this to aqueous ammonia, first of all, the silicon chloride will react with the water present. It will react with the water present, and so that will give us HCl and SiO2, silicon dioxide. Now this silicon dioxide, we know that this in fact will be a precipitate. This is not soluble in water. And after that, it's not really important to check out what the ammonia part of the solution does. The water has done enough to show the precipitate, right? So what two samples are they? Well, it is magnesium chloride and silicon chloride. Why is the ionic radius of a sulfide ion larger than the ionic radius of a potassium ion? Now, sulfide is S2 negative. It has a proton number of 16. And potassium has a proton number of 19 and has a 1 plus charge, right? Now, both of them have an electronic configuration of 288, right? If I were to use the simple electronic configuration. So you can see that number of shielding electrons is the same, number of shells is the same. The only difference is in the proton number and the nuclear charge, right? So the higher the nuclear charge, the more attracted the electrons are towards the nucleus, and so the smaller the ion, right? So in this case, it says the potassium ion has more protons in its nucleus than the sulfide ion, and that is correct, and that is why the ionic radius of the potassium ion is smaller. Which graph correctly shows relative electronegativity plotted against relative atomic radius for the elements sodium, magnesium, aluminium, and silicon? So now these four elements are part of period 3. So we will look at the periodic trends of electronegativity. Electronegativity, the trend across a period is that it increases, right? And the relative atomic radius, this actually decreases. And the reason for this, for both of these trends, is the same, that the number of shielding electrons and the number of shells remains the same, but it's the nuclear charge that increases, so it pulls the outer electrons towards itself, so the electronegativity increases, and the atomic radius thus decreases. So if I look at option A, silicon is further to the right of the periodic table, so it has the highest electronegativity and the lowest atomic radius, and we will keep going in this manner towards aluminium, then magnesium, then sodium. So option A correctly describes those trends. All right, so we have information about calcium carbonate and calcium hydroxide. First column, calcium carbonate is more soluble in water than calcium hydroxide. That is incorrect. So it's going to be no, right? Because carbonates are generally insoluble unless they belong to group 1 metals. Calcium hydroxide can be manufactured using calcium carbonate as a starting material. Yes, that is correct, because you can first decompose calcium carbonate to give you calcium oxide and carbon dioxide, and then calcium oxide can react with water to give you calcium hydroxide. So option B is going to be correct for this one. Q is a group 2 metal. An excess of QCO3, this is the metal carbonate, is added to sulfuric acid followed by filtration, right? So if it is added to sulfuric acid, we're going to get QSO4, right? And it says a sample of QSO4 is then obtained by evaporation of the filtrate. So because QSO4 is present in the filtrate, it passed through the filter paper after this reaction. It means that QSO4 is actually soluble, right? This is soluble in water. All right, so what could be the identity of Q? Now, obviously, we know that barium sulfate is insoluble, so it's not going to be option A or B, right? Now, option C and D, calcium or magnesium. It's going to be D. The reason is that magnesium sulfate is actually the most soluble, right, out of all the sulfates, and the solubility of sulfates decreases down group 2. So magnesium or calcium is the correct way to go. So X, Y, and Z are 3 elements in group 17, right? X2 has weaker covalent bonds than Y2. So what this means is, because X2 has weaker covalent bonds, it means it has a greater bond length. And because it has a greater bond length, that means atoms of X have a greater atomic radius, and so X will be further down the group than Y, right? The X2 has stronger instantaneous dipole-induced dipole forces between its molecules than Z2, right? So if X2 has stronger ID-ID forces, that means that it has more electrons per molecule. And if it has more electrons per molecule, it means more electrons per atom, in other words, more protons, and so a higher proton number. So X is further down the group than Z as well, right? So X is at the bottom, that's for sure. Y and Z, their relative positions are yet to be decided. Y2 is a stronger oxidizing agent than Z2. In other words, Y2 can be more easily reduced. In other words, Y2 can easily gain electrons. And the way to do that is to have a smaller atom with less shielding electrons so that the electron that is being gained can face greater attraction from the nucleus. So if you have smaller atoms, you have a smaller proton number, so Y will be above Z in this group. So what could be X, Y, and Z? Now for Y, we have two options, chlorine or bromine. So obviously Y is at the top, so I'm going to go with chlorine, right? Now for Z and X, Z comes above X, right? So Z has to be bromine, and then at the bottom we have X, which is iodine. So it's going to be option D. Chlorine reacts with aqueous sodium hydroxide, forming two chlorine-containing products. Which row shows the oxidation states of chlorine in the products under the conditions stated? So for cold sodium hydroxide, the products that we get are NaCl and NaClO, which are chlorine-containing. So the oxidation state of chlorine in NaCl is -1, and in NaClO it is +1, right? So automatically the first two options are incorrect. For hot sodium hydroxide, the products that contain chlorine are NaCl with an oxidation state of -1 for chlorine and NaClO3. Now in this case, oxygen, we have 3 atoms, so this is going to be -6. Sodium is +1 because it's in group 1, so chlorine turns out to be +5. So -1 and +5 are the correct oxidation states, and so option D is the correct one to go here. So a catalytic converter reduces the amount of pollutants in the fumes from a car exhaust, right? So which row identifies a pollutant and shows how it is removed by the action of the catalyst? Now, carbon dioxide being reduced to carbon, that would be problematic because carbon actually causes more pollution than carbon dioxide. So this is incorrect. Option B, carbon monoxide is oxidized to carbon dioxide. This is actually correct. Carbon monoxide is more harmful for human health and for the environment than carbon dioxide, so that's why it's oxidized, right? And we don't need to go to the rest of the options. So solid R is added to the solution of ammonium nitrate and the mixture is heated. A gas is given off which turns red litmus to blue. So the gas which turns red litmus to blue, there's only one gas that you've studied that does this, and it's ammonia, right? So if we add a solid R and we heat it with an ammonium salt, right, it releases ammonia. And this can only happen if solid R is actually a base, right? The reason is that ammonium ions are acidic. So they dissociate to give hydrogen ions and ammonia gas that is released. The hydrogen ion needs to be gained by a base so that the reaction is complete. So out of all these 4 options, only sodium oxide is basic. So we go with option C. So skeletal formula is shown of an organic compound. What is the total number of stereoisomers, including the one shown? So remember, stereoisomers means both geometrical or cis-trans isomers and optical isomers. Right, so if I look at cis-trans isomers, I need to look at carbon-carbon double bonds. Now this double bond will not show cis-trans isomerism because this carbon atom is bonded to two CH3 groups that are the same as each other. So I'm not going to consider this. I will consider this and this double bond because both carbon atoms in the double bond are bonded to two different groups. Right. So I will have different configurations. Right now, if I consider this shown over here, I have two hydrogen atoms on opposite sides of the double bond, so that's trans. And over here again, I have two hydrogen atoms on opposite sides of the double bond, so I have a trans-trans configuration. So I have other possibilities as well, such as cis-trans, trans-cis, and cis-cis, right? So I have 4 configurations for these two double bonds. And I need to look out for chiral centers for the optical isomers, right? So I have only one chiral center in this entire molecule, and it's this guy over here, right? Because it's bonded to a CH3, and then it's bonded to this part of the molecule, which is different from this part of the molecule, and then obviously the fourth is hydrogen, right? Now, I have these 4 configurations, but because of this one chiral center over here, I'm going to have mirror images for each of these configurations, right? So I have 4 cis-trans configurations times 2 because each has a mirror image, and so I will have 8 optical isomers. Sorry, 8 stereoisomers, both cis-trans and optical. So over here, it says how many outer shell electrons of the central carbon atom must be present for CH3 to act in these different ways. So it can act as an electrophile, free radical, and a nucleophile. So let's look at a free radical. So carbon is bonded to 3 hydrogen atoms. So that is 6 electrons being shared. And carbon needs to have 1 unpaired electron in its outer shell for it to be a free radical. So this is 2 plus 2 plus 2 plus 1. That gives us 7 valence electrons around the carbon for it to be a free radical. So option A or option D will be considered. For a nucleophile, we know that nucleophile is a nucleus lover, right? It needs to be negative to be attracted to a positive species. So we need 1 more electron to complete this, and so it will become negative, and we will have 8 valence electrons. And so out of these 2 options, we have 8 over here, and so option A is going to be correct. We don't need to check for the electrophile. All right, so this is a tough question, and need to pay attention to this. It says over here the compound Z has 2 chiral centers, and a sample of Z contains all 4 possible optical isomers. This sample of Z reacts with hot ethanolic NaOH to produce a mixture of only 3 isomers, right? Now this over here is a halogenoalkane. If it reacts with hot ethanolic sodium hydroxide, this is going to be an elimination reaction, right? So hydrogen bromide will be eliminated, and we get a carbon-carbon double bond. So 2 of these isomers are optical isomers of each other, right? So what is the formula of Z? So if I look at option A, we have a carbon bonded to the bromine over here. Now I have 2 options. Either I could remove a hydrogen from this carbon atom over here, right? And this will result in a double bond over here, right? Now once we have that, we know that in this entire compound, we will have 1 chiral center, which is this fellow over here, because it's bonded to a CH3 and a hydrogen. And if I were to draw a line to the opposite end of this ring, I would know that the 2 sides are not the same as each other. It's not a line of symmetry, so it is in fact chiral, right? So I have 2 isomers already that are optical isomers of each other. So that statement, 2 of these isomers are optical isomers of each other, is correct in this case. And if I were to do this again, I have this structure over here. Now the second option is to remove bromine and remove the hydrogen from the carbon atom on the right. And so the double bond will be over here, and as a result there are no chiral centers in this, right? So we have three isomers. We have two isomers that are optical mirror images of each other, and we have this particular isomer. So we have three isomers that are obtained from this reaction. So option A will be correct. No need to go further. So the free radical substitution reaction between methane and chlorine involves initiation, propagation, determination. Obviously, which row is correct? So involved in the initiation stage is homolytic fission, right? Because we have chlorine molecule that is being converted into chlorine free radicals. So this is by homolytic fission. And a radical produced in a propagation stage, now remember, nowhere in any free radical substitution reaction will you ever get a hydrogen free radical, right? It will always be either a hydrocarbon free radical or a halogenoalkane free radical or a halogen free radical, no hydrogen free radical. So it's going to be option B. So the alkene showed reacts with an excess of HBr via an electrophilic addition reaction. What is the major product formed? Now, over here in this double bond, it is this carbon atom that will bond with the hydrogen in HBr because it already is bonded to one hydrogen atom, whereas this carbon atom is bonded to no hydrogen atoms. So following Markovnikov's rule, this will bond to hydrogen, this will bond to bromine. Similarly, for this double bond over here, this carbon atom is bonded to two hydrogens, right? So this will also bond with the hydrogen in HBr. This will bond to the bromine according to Markovnikov's rule because this carbon atom is bonded to just one hydrogen, right? So if I write this out, I have this kind of a structure for my product, the major product of this reaction. Right. So if I count the number of carbon atoms in the longest carbon chain, obviously it's going to be 6. All options say so, right? It's going to be hexane, right? So I have 1, 2, 3, 4, 5, 6, right? Now the bromines are to be found at carbon atom number 2 and carbon atom number 5, right? If I count this the other way, it's also going to be carbon atom number 2 over here, the 3, 4, 5. So it's going to be 2,5-dibromo, right? So 2,5-dibromo, right? And again, because we have a methyl side chain over here, this is your methyl side chain, this is CH3. Now we want to make sure that the numbers are adding up to the smallest sum, the numbers representing the side chains, right? So I'm going to go with 2 over here and 5 over here. So this is going to be 2-methyl-hexane, right? So 1, 2, 2-bromo, and 2-methyl, right? So we have 2,5-dibromo, 2-methyl-hexane as our correct name for this. The diagram shows the structures of two halogenoalkanes P and Q, and both compounds can be hydrolyzed. So which row is correct? So a compound which is more readily hydrolyzed. Okay, so over here you can see that everything between P and Q is common except for the halogen that is bonded. So over here we have bromine and over here we have fluorine. So obviously the carbon-bromine single bond over here is going to have a greater bond length. So this is the weaker of the two carbon-halogen bonds. So this will hydrolyze more easily. So it's going to be P. And the reaction mechanism of this hydrolysis depends on the nature of this halogenoalkane. The carbon that is bonded to the bromine is bonded to 1, 2, 3 other carbon atoms. So this is a tertiary halogenoalkane. And because it's tertiary, it's going to follow the SN1 reaction mechanism. So option A is what we will go with. So over here we have a compound conene, and this is synthesized by reacting this dibromoalkane with ammonia, right? So this is actually a two-step process. So because we have a dibromoalkane, we have a carbon bonded to one bromine over here and another bonded to bromine over here. So let's say one of these bromines is substituted by an NH2 group from ammonia, right? So let's say this goes and we get NH2 in its place, right? Now NH2, just like the ammonia itself, also undergoes nucleophilic substitution reactions with halogenoalkanes. Now because we already have another halogenoalkane functional group, this halogen atom, already part of that molecule that hasn't been substituted yet. So this amine, this is an amine functional group by the way, will also substitute this bromine over here. So when this goes, this NH2 over here actually turns into an NH and it bonds to this carbon atom over here, and so we get a cyclic structure, right? So now using this concept, if I look at this carbon-nitrogen single bond and break it up, then I will know that before this bond was formed, there was a bromine over here and a hydrogen over here, right? And before this NH2 came as part of the molecule, there was a bromine in place of it all, right? So this was the whole process in reverse. So now if I look at the structure, we have a Br over here that is bonded to a carbon, which is basically a CH2 group, right? And so we have 1, 2, 3 other CH2 groups. So there's 4 CH2 groups bonded to this bromine, right? And then this carbon atom over here is basically a CHBr, right? This bromine over here is actually bonded to this carbon atom over here, CHBr, followed by CH2 twice, and then CH3. So looking at that structure, option D is what fits with this conene over here. So what are the color changes if we try to oxidize alcohols using either potassium dichromate 6? That is obviously going to be orange to green, right? So it's either option B or option C. And for acidified potassium manganate 7, the color change will be purple to colorless, right? So this was a very simple question, so it's option C for this one. So which reaction has a product that gives a yellow precipitate when treated with alkaline iodine, right? So first option gives us 2-chloropropane, which is warmed with dilute aqueous solution of sodium hydroxide. So with aqueous NaOH, this is going to be a nucleophilic substitution reaction, and the chlorine in chloropropane will be replaced with the OH group, right? So this is the hydrolysis reaction of a halogenoalkane that we looked at a few questions ago. So if I have chloropropane over here, so 2-chloro, the chlorine over here will be replaced by OH, right? And the rest of the structure remains the same, right? So if I look at this group over here, this group is basically CH3, CH, OH. And this is the group that gives a yellow precipitate with alkaline aqueous iodine. This is the group that we use this test for, and so option A is going to be correct. So M over here is reacted with an excess of LiLH4, and this actually is a reducing agent. It's a very powerful reducing agent that reduces pretty much every functional group that is reducible, right? So this carboxylic acid over here will be reduced to a primary alcohol. So this oxygen is gone, right? And this is an alcohol group, so this is not going to be reduced. And over here we have an aldehyde, and this will be reduced to, again, a primary alcohol group, right? So what is the molecular formula of the final organic product? Okay, so we have 1, 2, 3, 4, 5 carbon atoms, right? So that's C5. We have 1, 2, 3 oxygen, so that's O3, right? So keeping O3 and C5 in mind, that's going to be either option C or option D. Now, looking at the hydrogens, we have 1, and over here we're going to have 2, right? So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, right? So this is going to be C5H12O3. So option D is the final product. So which compound forms a precipitate when mixed with 2,4-DNPH reagent? Remember, this is used to test for the carbonyl group, and also forms a precipitate when mixed with Felling's reagent. Now this makes the carbonyl group specifically an aldehyde group that is being tested for, right? So over here, out of all of these options, it's only going to be option B over here that has an aldehyde group, which is over here. It's at the end of the carbon chain. This carbon atom is bonded to a hydrogen that is not shown in skeletal formula. That's your aldehyde group that will be successfully tested for. Which reaction is a redox reaction, right? Now, a lot of organic reactions are not redox reactions unless you specifically use a reducing agent or an oxidizing agent. And in this case, none of these options is that kind of reaction. But if I look at option C, this is reacting ethanoic acid with sodium. Now, whenever you react a reactive metal with an acid, whether it's a mineral or organic acid, it's going to give you hydrogen, right? So we know that ethanoic acid, when it reacts with sodium, it's going to give us hydrogen gas and sodium ethanoate, right? Now the redox reaction is that sodium goes from 0 over here to +1 over here, becoming part of this ionic compound, the salt. Hydrogen has an oxidation state of +1, being part of a compound, to 0 once it becomes an element, right? So this is in fact a redox reaction, so it's option C we're going to go for. So ethyl butanoate is a flavoring with a fruity flavor. Which row is correct, right? So the alcohol and the acid that react to form ethyl butanoate, right? Now, obviously, from the name, we know that ethyl tells us that the alcohol is ethanol, right? So ethanol is present in either option A or option B, which is this guy, right? And butanoate tells us that it's going to be butanoic acid, right? So butanoic acid has 4 carbon atoms, including the carbon atom in the CO2H functional group. So over here we have 1, 2, 3, 4, right? And same case for option B. So now the mass of water formed when 2.32 grams of ester is formed, right? So what we do over here is when this acid and alcohol react, they're obviously going to form 1 mole of the ester and 1 mole of water, right? So if we find the moles of the ester, we will find the moles of water, and then we can convert that into mass, right? So the moles of the ester will be 2.32 grams. This is the mass divided by the MR, right? And the MR will be, basically how we will calculate this is, we will take into account everything in the acid and the alcohol except for the H2O, right? The OH from the carboxylic acid is removed, and the H from the water, the alcohol, is removed to form the water, right? And so we have 1, 2, 3, 4, 5, 6 carbon atoms, right? So this is going to be 6 times 12. And we have 1, 2 oxygens, so that's 2 times 16. And if you count the hydrogens, it's going to be 3 plus 2 plus 2, so that's 7. And we're going to have plus 3 plus 2, so that's going to be 12, right? So plus 12, right? And this is going to give us 0.02 moles, right? And this is going to be the same as the number of moles of water, right? Because they're formed in a 1-to-1 ratio. So the mass of water will be the moles over here times the MR of water, which is 18. And so this is going to give us 0.36 grams. And this is option A over here. So cyclohexene can form addition polymers because of the fact that it contains a carbon-carbon double bond over here, right? Now, what will be the section of that polymer? So if I were to draw it something like this, so I have cyclohexene, right? So the double bond over here will be converted to single bond over here, and so these two carbon atoms will bond further, right? And this carbon atom then would form a bond with another molecule of cyclohexene, and this would look something like this, right? And so this is going to continue in this way. And if I just change the orientation a little bit of these molecules, it's actually going to be option C over here, right? Because if I imagine this to be the double bond, which is broken up to give 2 single bonds leading off from cyclohexene, the same thing over here. And so these two form a bond and continue the polymer chain. So it's going to be option C. Finally, we have 3 organic compounds, and which compounds will have a mass spectrum that contains a fragment peak at a mass to charge ratio of 43. So for this, all we need to do is to find the MRs of these compounds and see if they are greater than 43, right? So for ethanol is CH3CHO, right? The MR for this would be 2 times 12 for the carbons, plus 4 for the hydrogens, plus 16 for the oxygen, right? So this is going to be 44, right? Now, if I were to look at the structure for this, what I could do is remove this hydrogen, which is a part of the aldehyde group, and this is the fragment that could give me a peak at a mass to charge ratio of 43. So ethanol can produce a peak at this mass to charge ratio. For propan-1-ol, we have CH3, CH2, CH2OH, right? The MR for this will be 3 times 12 for the carbon atoms, plus 16 for the 1 oxygen, plus 8 for the hydrogens. And this will give us 60, right? If I did this calculation correctly, this is going to be, in fact, 60. Yeah. All right. So if I were to get a mass to charge ratio of 43, I need to remove a chunk of this molecule that has an MR of 17. And that simply is the OH group over here. So that's 16 plus 1, that's 17. So the rest of this can give me a peak at a mass to charge ratio of 43. All right. And finally, we have propan-2-ol. Now, if propan-1-ol can give a peak at a mass to charge ratio of 43, so can propan-2-ol. Doesn't make a difference, right? So option D, all 3 are going to give you a peek at m by e equals 43. And finally, we are done. We have finally delivered the ring to Mount Doom, and it is over. So I hope you enjoyed this walkthrough of the May-June 2022 Paper 1 Variant 2 of the A-Level Chemistry 9701 syllabus. And if you found it informative, you found it useful in your preparation for October, November, or any other exam you might be taking later, then do subscribe to the channel, do like and share this video, and do leave a comment on how you found this video and what you might suggest for the future. And inshallah, I will see you in the next video.